Hi everybody, and welcome to another video brought to you by PLCGurus.NET. So you're following along in our ControlLogix PIDE Essentials video series, and we are now in what is going to be the final video in this series. So we are in part 13, and if you have not watched the previous videos, I do highly recommend that you do so, so you know exactly where we are here. So in the last video, we got into some dead time modeling and looked at the impacts of dead time and lag time in our process. And if you recall, when we increased the dead time to 8 seconds, we were not able to recover our loop. It basically went into instability, and with the PID gain values that we had in there, we no longer were able to recover. So in this video, what we're going to do is we're going to see if we can make use of the auto-tuning feature of the PID enhanced controller to see if the controller itself is smart enough and can choose some optimal gains to get us out of that excessive dead time and lag time. Okay, so that's where we're going today, and as always, I have gone ahead and developed a PID tuning made easy manual that you can download, and I'll include a link in the comments section below, as well as this PID simulation panel that really will give you all of the test functionality that I'm working with here, save you some time to develop your own, I guess, and it'll allow you to simulate exactly everything I am simulating here so you can follow along in sequential order. So I'll include a download link to the sim panel as well in the comments section below so you can go ahead and get all of those things. Okay, so what I think we'll do, what we'll start with, is we'll just simulate where we left off in the last video. So if you recall, in the last video, we went into the DEDT instruction and put a value in the dead time of 8 seconds right here, okay? And we also went into the LDLG instruction and put a value of 5 seconds. And with the tuning parameters or the gains that we had set up, we noticed that when we put that dead time to 8 seconds, that our loop went into instability almost right away. And so what we're gonna do, maybe we'll just, to get started, we're gonna reproduce what we did in the last video to see that instability. And then we're going to go ahead and auto-tune this thing. So let's head on over to our trend and let's get that up and running. So we're going to start that. And let's go ahead, make sure our selector switch is in hand mode and start up our process. So we're now running in hand mode, and let's go ahead and compute a value this time that corresponds precisely to 105 degrees C, so that we have bumpless transfer, and see if that makes any difference, because last time, remember, we did leave a little bit of error there to see if the controller would recover, and it didn't. But let's implement bumpless transfer here and bring our PV right to our set point by inputting a correct percentage that our valve needs to be opened. So to do that, I'm going to use a percentage span calculation. And I'm going to put it up here on the screen so you can see precisely how you go about calculating these things. And this is a very useful formula, by the way, when you're trying to find a midpoint or find any point for that matter in a given span, okay? So as you can see here, the correct value or percentage that corresponds to a set point of 105 degrees C is 66.7 degrees. So let's go ahead and input 66.7. And we're going to watch our CV go right to that point immediately, which makes sense because we're in open loop hand mode and we are taking direct control over the position of the valve. And now you see the 8 seconds of dead time right in here and the lag time, that 5 seconds of lag to get us up to the set point. So we should see this thing climb right to set point after approximately or very close to 25 seconds because remember, it's 5 tau to get to 99.9% of our final value here. Okay, and look, it does model that first order lag that we were talking about. Okay, and I think we're just about there. So what I'm going to do, so now we have bumpless transfer, meaning we have zero error between our PV and our SP. And let's go ahead and kick this thing into auto this time and see what happens. Okay, so we had zero error, so this is a little bit different than what we saw last time actually, isn't it? Because remember, last time we only brought it to 50% CV hand, so we had some error in there. And when it was trying to compute and close off that error, it went into instability. So I think this time, in order to get us into instability, we're going to actually have to hit it with a disturbance. So let's hit it with that step input of 10 degrees C. So we're adding heat energy into our process from an external source, and it should follow now that our output actually starts closing off our valve, right? Because it doesn't need as much steam now to maintain that set point. And look what's happening here. So now I would expect that we're going to get into that instability and into that oscillation of overshooting and undershooting and overshooting for reasons we explained in the last video. So let's go ahead and just let that run for a minute just to show that we are in that unstable region now. And it makes sense because our DT, our dead time to leg ratio, is greater than 1, and we said that if that ratio is greater than 1, that this loop is going to be very difficult to control. Not impossible, but difficult. So let's go ahead and let that run just for 1 minute, and then we'll just stop it, and then we'll get set up for an auto tuning. So what I want to do, we see that any change or any disturbance that affects our process, we go into instability right away. So that's obviously not acceptable for a real process, and we need to tame this loop somehow. We need to get this thing into some kind of stability or reasonable response if we're going to try to manage that dead time of 8 seconds with a 5-second lag. Okay? Maybe, we've done everything possible to mitigate the dead time in the system, but this is what we have. So we have to find a way to get this under control. And we're going to do that by using the auto-tuning functionality of the PID loop controller. And we're going to hopefully see that the controller is smart enough to compute a set of gain values that is going to get this thing back into some stability. So I think that's far enough. We'll stop it there, and then we'll get set up for our auto-tuning. So let's head back over to our loop control routine. And the first thing we're going to need to do, and what we've neglected to do until now, is set up an auto-tune tag for our PIDE controller here. So I'm just going to right-click the question mark and go new tag, and let's call it auto-tune. And notice it gets the correct data type right away because we are creating the tag in the instruction we intend to use it. So it did correctly assign the data type PIDE auto-tune tag. And okay, so it didn't show up there. So I think it's because we have to go and edit the rung now. So let's go in here, double click it down. It should be created. There it is. Yeah, so we just had to go into edit mode to actually add it to the controller. And there we go. So the auto-tune tag has now been defined. And now we can go ahead and actually auto-tune this thing. So there is a whole set of steps that we're going to need to do. And I think we'll probably have to run through this a couple of times to get it just right. Let's get going. So I'm going to go into the controller here, and now we want to head on over to the auto-tune tag. So the first thing we need to do is we need to acquire the auto-tune tag that we just created. And the reason for this is we can have multiple loops use the same tuning tag. I guess it's more efficient to do that. And so all we have to do is make sure that, number one, it's not already being owned by another controller that's using it. And if it's not, we go ahead and acquire it. And once we're done with the tuning procedure, we can go ahead and release that tag so it's available for another loop controller to use it if it needs to. Okay, so let's go ahead and acquire that one more time. And now you see we have some options here. So the first one is the process type. So we are modeling a temperature control process. So the default here for us is perfect because we are trying to maintain the temperature of a processed liquid in a vessel using steam, right? But if you click on the little drop down here, you can see there are many other types of processes here that we can set up and use to do an auto tuning. So pressure, flow, level, position, velocity, whether it's an integrating, non-integrating, unknown process, okay? So let's go ahead and leave the default temperature. The next thing we want to do is we want to use a PV or set a PV change limit. So I'm just going to hit the help button here just so we can see what the actual help file tells us about these two settings. So the So we have the process type, temperature. That was pretty obvious. So the PV change limit. So enter the value of the PV tune limit auto tune parameter. If the PV exceeds this limit during the auto tune process, the auto tune is aborted. So if you're auto tuning a process that is already running, it may not be desirable to allow the PV to change outside of some kind of process limit, because you could potentially ruin the batch of whatever it is that you're heating or fermenting or what have you while doing the auto tune. So you may want to say, hey, okay, I'm going to do an auto tuning on this running process, but I cannot allow the PV to change outside of this acceptable limit. Okay, so for us, I don't really care. So let's just go ahead and put, you know what? Our limit right now is for 120 degrees C. That's the maximum we want to allow the PV to change, because that is actually the limit that we defined in here. Okay, so that's fine. But for you, it may be something much tighter than that, depending on your process. All right, and likewise, the CV step size. So let's just read it. Enter the value of the step size auto tune parameter. This defines the size of the step change to the output that the auto tune will apply to the CV when the auto tune process begins. So again, if this is a running process, it may not be desirable to allow the valve to move beyond some percentage that you define, because you could damage something. If this is a motion application, for sure, you may not want to bump the motor too much, or what have you. So again, these are just, if you're auto tuning a running process, these are useful to put in there to say, hey, I want to try and auto tune this thing, but if it needs to go outside of the limits that I'm defining here, we're going to abort it, because I don't want to throw potentially all the product I have in my system. So let's go ahead and put a CV step size, and this is going to be something small. So what the auto tune test is going to do, it's actually going to bump the output and then compute based on the feedback, the PV change, what the optimal gain values need to be. So I don't want to get too heavy into the complexity of how it's doing it, but just know, and we're going to see it in the trend, it's going to perform a bump test, and then while it's relaxing back to its new set point, it's going to be computing the process dynamics, essentially, to determine what the ideal gain values are going to be. Okay, so let's go into the auto tune. Oh, we have to apply the changes first. Yes. And now when we're ready to start auto tuning, we want to come back here and hit the start button. And then it's going to go ahead and compute, if everything works properly, 3 sets of gains depending on the type of response that we want. So it's going to compute 3 sets of gains for a slow, medium, or fast response. So we're going to choose one of those 3. You know what? We're going to choose the slow response, and it's not going to be as aggressive. And we're going to see if we can successfully auto-tune our way out of that excessive dead time and lag time that's in our process right now. So I hope that's clear. Let's close this off. Let's click OK here. Let's get our trend set up. We're going to close this too. Let's get our trend set up, and then we'll start. So what I should also mention too is that the auto tuning procedure is actually an open loop type tuning procedure. So what we want to do, so let's go ahead and zero out this temperature disturbance initially at least, and get that to 0. Our process has stopped. We're in hand mode. Now let's go and get our trend going here. So let's run the trend. And you can see here that PV is going to settle out. So let's let PV settle out here. And you know what? I'm going to pause the video while it does that, because it's going to take a few seconds to do that. Okay, so I think our PV is now settled out, and our disturbance is at 0, and our set point is at the 105 degrees C. So this time, what I want to do is I want to put a value again of 50% in. The reason we don't want to do a bumpless transfer here is we want to give the controller and the auto tuning procedure a little bit of air in order to work with. Okay, so let's go ahead and bump this up. Well, first, before we do that, let's start the process. Let's put a value of 50% in CV hand, and let's let that PV settle out very near our set point value, which is not going to get to the set point. We know it's going to get us to around 97.5 degrees, right? So we don't want to do this too early, because if the auto tuning procedure detects too much movement in the PV while it's doing it, it's going to go ahead and abort the process. So what I would caution you is make sure that the PV is reasonably settled at its value, leave a little bit of air in there, and then start the tuning procedure. So let's head back over to the loop control. Let's go back into the auto tune tab, and now let's go in and auto tune this thing. So I'm going to go ahead and start the auto tuning process. Okay, so you can see its execution state is in process or in progress, and the auto tune status right now is okay. So we'll go back to the trend and analyze it in a second. Let's see if this thing can complete. Hopefully it will. So it's measured some dead time here of 8.6 seconds. So there's probably a little bit of scan. And look, so it says the observed PV change was too small, so it gave us a warning there, but it did successfully give us 3 sets of gains. And notice it did compute a small derivative value there for us. Okay? And so what we want to do here, we're going to select slow response, and we're going to say set the gains in the PIDE instruction itself. So it's going to take the proportional integral derivative and write them to the general config PIDE parameters for us. So let's do that. Let's close. Let's go to the general tab just to see that they took. It did in fact take. Let's click OK, and let's go back to our trend and see what happened. So you can see here, I'm going to go ahead and kick the process into automatic mode. Okay, so you can see here, so now it's trying to get us back to our set point. When, remember, before we couldn't. With the dead time we had, we went right into instability. So let's see what happens here. And notice the bump test it performed on CV right here. That's when it was performing its auto-tune procedure right here. So we're going to let that run. Maybe we'll zoom out just a little bit. Let's go to 4 minutes. There we go. And hopefully, with any luck, the auto-tuning found some ideal tuning parameters for us, some ideal PI and D gain values that is going to get us under control. And it looks to me, although it's taking long, we have a lot of dead time and lag time in our process here. Although it is taking a long time to get there, it is getting there, isn't it? Yeah, so we're pretty much at set point right now. So I'm going to go ahead and just hit this with a disturbance now and see what happens. So there's my step. Let's see if it pushes us into oscillation again. There's the dead time, and now we're responding. And we overshot the set point a little bit, but remember, let's see if it actually gets us back and stabilizes. So this is looking much better than what we had before, isn't it? So we're gonna lose that trend. I'm gonna zoom us out just a little bit more. Let's go to 5 minutes. There we go, and then we should be able to see everything. So you can see, although it is taking a long time, it's very sluggish. We have effectively tuned our way out of an excessive dead time and an excessive lag time. Now, a lag time of 5 seconds is pretty excessive, I would say. I'd be looking at some reasons why things are doing that, but who knows? Depending on the process, maybe it's okay. Okay, so I think we've effectively auto-tuned our way. I think it's safe. Let's stop that. I think it's safe to say that we have some stability. We were able to get our loop under control, and we did so by leveraging the auto-tuning function of the PID enhanced instruction or controller. So again, I hope you found this video informative. In fact, I hope you found this series informative, and you're a little bit more knowledgeable now about how to effectively implement a PID closed loop controller in a Logix 5000 platform. So again, I hope you liked this video. Please do like and subscribe to our channel. Head on over to https://PLCGurus.net and become an active member in our community. We are the fastest growing, or the internet's fastest growing community of professional engineers, technicians, and technologists, and we're looking to grow. So please share, please like, please subscribe, and again, thank you for watching. If you have any questions, comment section below, and I'll try to get to them. Thanks a lot. Bye-bye.